Hi everyone, today we're going to start chapter 17, which is going to begin a series of a deep study and understanding of oxygen-containing functional groups. We're going to start off pretty basic. In this chapter we're talking about alcohols and phenols, and this will be a three-part series for chapter 17. There's a lot of information in there, as you can tell. There's over 60 slides. However, a lot of it's going to be review, which will be very good. We're going to talk a little bit about, acidity and boiling point based on intermolecular forces, review over some nomenclature, as well as talk about some reactions that you've already seen in the first semester of organic chemistry. So I'm going to break it down into three parts, so that's a little bit easier to digest. But like I said, this will be great. This chapter is a fantastic review for all of us, right? Just to go over some of those things that maybe we've forgotten. It's still there, but we just got to bring it forward in our mind. So remember that alcohols contain an OH group, and if some of you are in cellular and molecular biology or biochemistry, that means, they call it like a hydroxyl group, but we're going to refer to it as an alcohol. And an alcohol or OH group is connected to an sp3 hybridized carbon atom. And they're important as solvents. You've already used a lot of these alcohols before in the laboratory, and we're going to see, especially when we study carbonyl chemistry, that they're going to be important synthesis intermediates. So you're going to form some sort of kind of alcohol as an intermediate, and we'll talk more about that later on. And then also within this chapter, we're going to discuss more about phenols. I know we did just talk about aromatic compounds in chapter 15 and 16, but more specifically, we're bringing phenols back in, which is an aromatic ring with an OH group, just to kind of compare them to their aliphatic alcohol counterparts. Okay, so you get some more review even from those most recent chapters that we just studied. Okay, so I just want to go over some common examples that you're already aware of. Methanol we use all the time in lab, has the formula CH3OH. Also known as methyl alcohol, and it's a very common solvent. It's a fuel additive, and it's produced in large quantities in the industry. Ethanol also we use to wash our glassware, and it's got the molecular formula CH3CH2OH, also called ethyl alcohol, very common solvent. It's also used as fuel, as well as it's the alcohol that's in alcoholic beverages. Phenol, which has the formula C6H5OH, that C6H5 is that aromatic ring. It's got diverse uses, which we'll be able to discuss a little bit more in this chapter. And its name, or phenol, is a name given to a general class of compounds. We use it as the suffix name or the parent name. Instead of saying hydroxybenzene, we use the common name phenol if you have an OH, and the OH on the aromatic ring is the highest priority group. Then the ending will be phenol rather than hydroxybenzene. And then finally, we also have talked about this already, maybe you don't realize it, but in the first semester of organic chemistry, we talked about enols back when we discussed triple bond chemistry or alkynes. And those are enols or OHs that are attached to an sp2 hybridized vinylic carbon. And they are not very stable. Remember, we talked about keto-enol tautomerization. It may be good to refer back to that if you have questions about it, or you're like, oh, what is she talking about? We'll talk more about it again, but it'll be good review. So keto-enol tautomerization. And remember, enols weren't very stable. So that's why when you see this photo here, this picture here, we have the brackets around it, because generally they're intermediates, and so they tautomerize into the keto form. This is showing you an example of phenol, and here's an example of an alcohol. Okay. So I always like to begin these chapters with, why do I care? What's my motivation? Well, the motivation for why you should care is, mainly about this chapter is because we are beginning to study oxygen-containing functional groups. We're going to do lots of review, but we're setting you up for success when we talk about carbonyl compounds, and that's like chapters 19 through 23. That's the heart of 12B, is understanding oxygen-containing functional groups. So you really want to master this material now so you feel better later when we get to that more difficult reactions. And in addition, alcohols and phenols lie at the heart of biological chemistry. So many of you are going towards more of a biological field of study, and so you're really interested about how does chemistry relate to the body or to drugs or that sort of thing. And so, these you'll definitely run across in your future biology or biochemistry classes. For example, we have phenol. You're going to see that very commonly used not only in organic chemistry but biochemistry. This is methyl salicylate. This is basically that oil of wintergreen. So if you chew gum that has a wintergreen flavor, it probably has this chemical in it to give you that flavor and that smell. Remember this key functional group here is an ester. So not only does it have an alcohol group, it has an ester. And that's also the reason why the ending for that name is 8 and not OL. And we'll talk about priority naming later. But esters have a higher priority over alcohols. Okay, so the ester got the number 1 there. We'll talk more about it. It's more of a common name anyways for that particular group. And then finally, you're going to see uracils probably in your future. And just, they have different R groups of long kind of alkyl or like alkenyl side chains. But basically, these are the allergic constituents of poison oak and ivy. So definitely going to see these in the future. It's important that you understand them now. And in order for us to discuss them in great detail, we need to have a systematic way of naming them. So I'm going to go through nomenclature. And there are general classifications before we get really deep into how do you name alcohols versus phenols. But there are general ways to classify alcohols based on the substitution of carbon that the alcohol is attached to. So for example, if the alcohol is attached to a CH3, then that's methyl alcohol or methanol. If the alcohol is attached to a carbon that has one other carbon attached to it, then it's a primary alcohol. If the carbon's attached to 2 R groups, it's secondary. If it's attached to 3 R groups, it's a tertiary alcohol. So we're looking at the substitution of the carbon it's attached to. And this is very important that you understand this type of classification system. An understanding is it primary, secondary, or tertiary. We classify it based on the carbon it's attached to. Okay. You notice here that this carbon, which is secondary, has 2 R groups. This carbon here, which is tertiary, has 3 R groups attached to it. So you want to understand that because I'm going to refer to primary, secondary, and tertiary, and want to make sure that you can visualize what I'm talking about. So a lot of these IUPAC rules we already know. So every time we go through nomenclature from here on out, I might teach you something a little bit new, a little bit different, like different ending names and all that sort of thing. But you really follow the same methodical system that we did in the first semester of organic, which is, first of all, you want to select the longest chain containing the hydroxyl group. I'll explain why that is in a little bit. You may be thinking, oh, okay, I just thought we found the longest carbon chain, period. No. We're going to have priorities, and so a hydroxyl group or OH group is going to have a higher priority. And once we do that, we derive the parent name by replacing the E ending of the corresponding alkane with OL. I'm going to go through kind of like what we do and then show you examples. We're going to number the chain from the end nearest to the hydroxyl group, and then number the substituents according to the position on the chain, listing everything in alphabetical order when we write out the full systematic name. Okay. So as you can see here, we started numbering closest to the alcohol group, 1, 2, 3, 4, 5. So originally that would have been pentane, but we dropped the E and replaced it with OL. So therefore we have pentanol. And there's also a methyl group, so this would be 2-methyl-2-pentanol, or I actually prefer the new naming system, which has the 2 directly in front of the suffix ending OL. Okay, 2-methyl-pentan-2-ol. This will be very helpful with when you have alkenes in there as well, and you'll see that in a few minutes. Okay. This one here is a cyclohexane, and it's a disubstitute cyclohexane, so it does have stereochemistry. We can use cis or trans. You could also use R or S if you wanted to here. But cis 1,4-cyclohexane diol, because it has two alcohols here, it's not just a cyclohexanol, it's a cyclohexane diol. Now, a lot of students get confused. Why did we not drop the E, Dr. P? So, cyclohexane. You don't drop the E. The reason why that is because the suffix ending begins with the consonant. And so you keep the E if we have a consonant that's about to attach to it. For this one, the suffix ending begins with a vowel. So we drop the E so that we don't have those two vowels next to each other. It's more of an English thing. I do realize it's a little confusing, but that's just the way it is. So this is a cyclohexane diol. I prefer you write the numbers right in front of the suffix ending. So cis-cyclohexane 1,4-diol. All one word. Remember to use hyphens to separate letters and numbers. To use commas to separate numbers. Okay? And then finally here, you'll notice, now this is why I want to show this one, in particular, because a lot of times I get students wanting to say, well, this benzene ring looks so important. It's, it does look very important, right? It's benzene. However, and it's also got the longest carbon chain in a sense, like 6 carbons, right? But what I'm going to get into and discuss is that it doesn't matter here what the longest carbon chain is. That longest carbon chain must contain the alcohol group because it's a higher priority group. Definitely higher priority than benzene. So therefore, the longest carbon chain that contains this group is got 4 carbons long, so that would have been butane, but we dropped the E because we're replacing with OL, and so it's butanol. And remember, if benzene's a substituent that's directly attached to the longest carbon chain, or the highest priority group there, then we refer to it as a phenyl group. So this is a 3-phenyl 2-butanol. Or, what I prefer is 3-phenyl-butan-2-ol, having the number directly in front of the suffix ending. Okay? And remember that when we have a phenol and the highest priority group is the alcohol, we use that for the parent hydrocarbon name, not benzene. You have to use the common name. That's what's been accepted by IUPAC because it's been historically used for so many years, even before IUPAC came into place. Okay? And remember to name the substituents on the aromatic ring by their position from the OH. And that's something that we just practiced. I'm not going into a lot of detail right now, but we'll definitely be practicing the laboratory work sessions. Your textbook's got great practice problems. So definitely want to make sure you're practicing nomenclature because they're easy points on the exam. It just takes practice, but if you don't know the rules, you won't do very well. Before I move on, I want to talk about what I've been alluding to this whole time, and that's talking about priority. So IUPAC came up with a list of functional groups in priority, right? The highest priority functional group is the carboxylic acid. And you're going to have to learn this list. And I don't believe in memorizing, so I say practice, 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 so that you understand it and it's more of second nature to you. And we will definitely be practicing as we learn each of these functional groups. The second highest priority group are esters, followed by acid chlorides. The next one are amides, followed by nitrile groups, aldehydes, ketones, and then alcohols. So now you can see where alcohols fall into place. Followed by thiols, which are the analogs of alcohols but contain sulfur. Then we have amines, followed by alkenes, So you see here, alkenes are not even that, high on the list. Alkynes. We have alkanes, ethers, alkyl halides, so those are all like the halogens, right? Alkyl halide, the nitro group, that's the NO2 group. It's last on the list, okay? And so therefore, the functional group with the highest priority will be the one which gives the suffix to the name. Now you may be wondering, well, how did IUPAC come up with this list? Is there any rhyme or reason? Really, there's not rhyme or reason to the order of this list. The only thing I can tell you is that generally speaking, the more oxidized groups tend to have a higher priority. So for example, carboxylic acid's really oxidized, right? This is a higher priority than, for example, a ketone, okay? So that's kind of how it will help you to remember it, but actually just practicing these and practicing lots of different problems, and as we introduce more functional groups to you, you'll get to practice, competition between the two or between three functional groups. Which one has the highest priority? Right now, all you have to worry about are alcohols. Right now, currently, we're at the alcohol stage. Okay, eventually we'll get to the ketone and aldehyde stage, and so on and so forth. Okay, let's go ahead and practice. Pause the video, give the names, the IUPAC names for the following compounds, and then come back and check your work. Good. Hopefully you've had a chance to do this, so you're just checking your work, no cheating. Make sure you do it on your own first. Let's do the first one. Looking at this compound here, the highest priority group is what? Definitely the alcohol. So that's where you're going to start numbering. We're going to number so that now that's number 1, but the substituents get the lowest number. So I'm going to number counterclockwise because that gives you the second substituent, the number 2, 3, 4. What's the parent name for this particular compound? It has to be phenol. Good. And the other substituents we have are 2, ethyl, and 4, nitro. Excellent. So I got all the pieces together. Now I just have to glue them together in what order? In alphabetical order. So therefore you have a 2, ethyl, 4, nitro, phenol. Now students ask me, well, Dr. P, do I need to include the 1? It's not necessary in this aromatic ring structure. It's assumed that if the OL is the suffix name, then the alcohol's at position 1 anyway. If you do include the 1, I won't take off. Then that's just good practice and helps to make sure that you'll never forget the suffix numbering system. So it's up to you. And then this one here, what was your longest carbon chain? How many carbons long? Okay, good, 7. And you numbered closest to which group? To the alcohol, okay? You don't want to number closest to the alkene. Remember, alkenes weren't the highest priority, right? So we're going to number toward closest to the alcohol. So 1, 2, 3, 4, 5, 6, 7. Originally, this was a heptane, if we just talked about the alkane. But it has a double bond. So it technically would go from heptane to what? Heptene. So even though the alkene is not the highest priority group, it's still in the suffix ending, okay? That doesn't change. So it goes from heptene to heptene, but it's not heptene because the highest priority group is an alcohol. So this, we drop the E because we're replacing it with OL. So that's how you derive the parent name. This is a heptenol. And we also have a 6-chloro. And we have some stereochemistry to worry about here. We have 2 cases of stereochemistry to worry about. Let's focus on the first one. What kind of stereochemistry do we have here? It's going to be R or S. What's the highest priority group? The alcohol, good. The next highest priority group is the rest of this chain. And the third would be this one, and then the hydrogen's 4. It's already in the back. Made it a little easy for you here. And so if we look here, it's going counterclockwise. So what kind of stereochemistry do we have? It's a 3S. Good, counterclockwise. Now, looking at the double bond here, what do we have? What kind of stereochemistry do we have to worry about here? E or Z, right? And I always taught you with E or Z, kind of like snip it in half, and you're comparing that priorities of the groups that are directly attached to one of the carbons. So chlorine versus carbon, which is higher priority based on atomic number? Definite chlorine, so this would be the higher priority group. This would be the lower priority group. Carbon versus hydrogen, definitely the higher priority group is carbon. The lower priority group is hydrogen due to atomic number. The higher priority groups are on the same side. I always say same side, right? Because that's therefore what kind of stereochemistry? Z stereochemistry. So that would be 5Z. So there are all of our pieces of the puzzle. Okay? And therefore we want to combine them together. When we write the stereochemistry up at the front, it's always in parentheses, and you write it in numerical order, not alphabetical order. So, you want to write 3S, 5Z. So it just, based on the numbers, don't worry about the letters of the stereochemistry. Okay? So we have 3S, 5Z, and 6-chloro. Okay? And it's a hept. And then right in front of the double bond, we need or the suffix ending for the alkene, a 5, because that's where the double bond starts. 5-ene hyphen. Then where is the alcohol located? Position 3-ol. So this is a 3S 5Z 6-chloro hept 5-ene 3-ol. You can make a song out of it. Okay? So this is the reason why I like the new naming system. Okay? Because the number's directly in front of the suffix name. Whereas before, it would have been a 5-heptene and then a 3-ol. It gets a little confusing, like, okay, is the 3 in front of the ol or whatnot? So just always use the new naming system when you do these problems. Okay? Now I want to move on. Make sure you practice that nomenclature. You want to get full credit on those points there. But now I want to establish some structure-property relationships. A lot of this is going to be review for you. And if it doesn't feel like review, then make sure you come see me during office hours or ask questions during the laboratory work session periods. Because a lot of this is based on general chemistry knowledge as well as the first semester of organic. So the first thing I want to talk about are boiling points. Okay, we know that the structure around the oxygen, the alcohol, or phenol is similar to that of water. It's sp3 hybridized. 2 bonds, 2 lone pairs. However, alcohols and phenols have much higher boiling points than analogous alkanes and alkyl halides, much higher boiling points. Why do you think alcohols and phenols have high boiling points? Think about it, try to answer it. It's okay if you're wrong. Really think about that question. Hopefully you said the reason why alcohols and phenols have higher boiling points is because they have hydrogen bonding. Okay. it all comes down to intermolecular forces. So intermolecular forces I will abbreviate to save time IMF, right? And these intermolecular forces must be overcome for a molecule to break free from the liquid and enter the vapor state. Okay, and the trend that you should know, and that's going to help you, the structure-property relationship, as you increase the intermolecular force, as it gets stronger, it's going to be harder for that particular molecule to break from the liquid to the vapor state, so therefore the boiling point will be higher. Same thing for melting point. As you increase the intermolecular force, melting point also increases. But we're going to focus mainly on boiling point right now for these particular compounds. Okay? Just to review, like I said, this should be more general chemistry knowledge and first semester organic knowledge. But what are the four dominant intermolecular forces? We can break them down into more than just four, but we're just going to focus on four and be very general and simplify. What's the strongest intermolecular force, which is also an intramolecular force? Ionic forces, good. Or ion, anything that has ionic or ion dipole, those ionic forces are very strong, because usually that means there's an electrostatic attraction between a positive charge and a negative charge, right? What's the next strongest intermolecular force? In general, it's going to be hydrogen bonding. Good. And remember, hydrogen bonding is hydrogen that's bonding to a nitrogen, an oxygen, or fluorine. So you're going to see lots of hydrogen bonding, especially in organic and bioorganic compounds, because a lot of them contain nitrogen and oxygen. What's the next intermolecular force in terms of strength? These are dipole-dipole forces. Good. So dipole-dipole forces occur with polar molecules. So if you know you have a polar molecule but doesn't have hydrogen bonding, then it probably just has dipole-dipole intermolecular forces as its strongest dominant intermolecular force. And then finally, the weakest of the intermolecular forces are dispersion forces. Now, every compound has dispersion forces, but it's the dominant or the strongest intermolecular force that determines its properties. So even though, for example, water has dispersion forces, its strongest intermolecular force is hydrogen bonding, and that's the reason why water has such a high boiling point for such a small molecule. Okay? So let me give you an example. So let's do an example. Let's say I have constitutional isomers, and I ask you to rank them based on boiling point. So for example, I have dimethyl ether and I have ethanol, right? Same molecular formula, different structures. Which one would you predict would have the higher boiling point and why? Hopefully you said ethanol. This would have the higher boiling point. The boiling point of ethanol is about 78 degrees Celsius. The boiling point for dimethyl ether is about negative 24 degrees Celsius. So it's extremely volatile, right? There's a huge difference there, and it all comes down to intermolecular forces. What's the strongest, most dominant intermolecular force with ethanol? Hydrogen bonding. Good. What is the strongest, most dominant force for dimethyl ether? Only dipole-dipole. Good. It cannot participate in hydrogen bonding, right? So it's really important that you understand that. If you're having difficulty being able to determine, okay, is it hydrogen bonding, or is it dipole-dipole, or is it just dispersion or ionic? Like, please come see me. Like I said, a lot of that is review from general chemistry, from 1A, the first semester of general chemistry, as well as we did cover a little bit in the beginning of organic chemistry last semester. So if you do need help, come see me, ask questions. I want to make sure you understand the structure-property relationship. Because rather than memorizing boiling points, which is impossible for all the compounds you learn, I want you to understand the patterns and trends based on their structures. Okay? So please come see me if you need help. And then as you see here, or maybe not see, let me erase. I had a nice pretty figure here and then I wrote all over it. There we go. As you see here, this is just showing you alcohols and how they hydrogen bond. Remember, intermolecular forces are not actual bonds. They're just the way these particular molecules interact with each other. It's the interactions between many molecules. So partial negative oxygen atoms are attracted to partial positive hydrogens of other molecules. You can see how they're attracted to each other. You can definitely see it in the electrostatic potential map where hydrogens are blue and oxygens are red. So remember, the key theme of organic and any chemistry is that opposites are attracted to each other. It's the driving force. Okay? Now we're going to move on talking about acidity and basicity. And this is probably one of the most difficult concepts for students to really master in my class. You would think, really? We've been doing this since general chemistry. You know, we did it definitely in the first semester of organic, but sometimes students still struggle even second semester because it's not as easy as it looks, right? So it's important that we talk about it, we discuss it more, and when you get to the ACS chapter of acids and bases, you'll understand why I mean it's not so easy. It's not trivial like you would expect it to be. But it takes some practice, and like I said, I'm going to help you develop patterns so you fundamentally understand what's going on, not just memorizing pKa's, because that's impossible. It's just not worth your time, and you have enough to put in that brain of yours and to store. So let's talk a little bit about properties. Now, alcohols and phenols are weakly basic and weakly acidic. If a molecule or compound acts as an acid or a base, it's known as to be what? Amphoteric. Good. So they can act as an acid or a base depending on what you're reacting with. Alcohols are weak Bronsted bases. What's a Bronsted base mean? Bronsted base means that it's a proton acceptor. Which means in the presence of a strong acid, we can yield what's called an oxonium ion. So something that you'll see in the future, maybe used as an intermediate. Where this alcohol, these lone pair of electrons pull off this proton, kick off whatever the leaving group is, and makes that anion. And so the oxygen ends up with a +1 formal charge, and that's why it's called an oxonium ion. And we can see the same thing with phenols here. This means aromatic. You may be like, what's AR? It's another way of saying aromatic, or they could have used pH there too. Plus the acid to give this particular oxonium ion, and it has a leaving group that's associated with it. You notice the equilibrium is not very far to the right. It's a very weak base. It takes a strong acid to protonate it. On the other hand, we can also have them behave as weak acids or weak Bronsted acids, which means they can transfer a proton or be proton donors. So Bronsted acids are proton donors. And in the presence of water, we can transfer a proton to water in a small amounts, right? It's a weak acid. And when it does that, it produces hydronium ions in solution, as well as an alkoxide anion or a phenoxide anion, depending if you're doing aromatic or aliphatic, in solution as the conjugate base. And we're going to talk a lot about these. This is the conjugate base of the alcohol, right? And you can see here water is pulling up that proton. Those electrons come here to make the alkoxide anion. You're left with the hydronium ion. You probably worked a lot with these types of reactions back in second semester of general chemistry when you studied weak acid and base equilibria, right? You did all your rice tables or ice tables or whatever your professor called them. Okay, how do we quantify acidity? We do it in terms of Ka, right? The acidity constant Ka measures the extent to which a Bronsted acid transfers a proton to water. Okay? Remember when you do the reaction, it's Ha plus water. This is a generic weak acid equilibrium reaction that you used in second semester general chemistry to make A minus conjugate base plus the hydronium ion. And when you do any kind of equilibrium constant expression, it's always what over what? Products over reactants. Good. So it's always products over reactants. The products are the conjugate base, the hydronium ion, over the reactants. Water not included because water is in the liquid state. Liquids and solids, remember, are never included in the equilibrium expression. We talk about Ka a lot in second semester general chemistry, but in organic, we talk more in terms of pKa. Remember, pKa is defined as the negative log of Ka. The reason why that is that talking about relative, acidities is way more convenient presented on a logarithmic scale, pKa, and rather than talking about Ka, which is like, for example, it could be like 1 times 10 to the negative 7th. And you're like, okay, it's hard to think in terms of scientific notation. So pKa will be a little bit more manageable in doing so. I just want to make sure, this is review, what is the relationship between pKa and the relative strength of the acid? Okay, the smaller the pKa, the what? The stronger the acid. Good. It's important that you know that trend, because if I do present you with some data, you're able to understand, okay, the smaller pKa materials are definitely stronger acids. Good. I just want to make sure you understand that all of these like equilibrium constants and that sort of thing is related to thermodynamics. The differences in pKa correspond to differences in free energy, telling you if a reaction is spontaneous or not. Remember that delta G, which is Gibbs free energy, is equal to negative RT natural log of K, or Ka, or whatever KEQ is. So if you understand what your equilibrium constant is, then you have a better understanding of where you're at in equilibria and in terms of is this reaction spontaneous or not. Now, we're not going to do a lot of math in this class, so you don't have to worry about doing these calculations again. But when I was a student, it helped me to know the formulas in order to derive those trends and understand it. So if I got stuck on an exam, I'm like, okay, is it the smaller the pKa or the higher the pKa? You can derive it yourself if you understand the mathematics behind it. Okay, so remember my class is more theory-based, more conceptual, but there's a lot of math that supports what I'm stating, okay, that you can still use, that you learned back in general chemistry. So for all you math people out there, don't be afraid to use it, okay? Okay, so in the next slide, I'm showing you kind of examples of, different kinds of, acidity constants for alcohols and phenols. And like back in the day, some professors may have been like, memorize them all. It's good for you, right? No. That's not my philosophy as a teacher or professor. I want to make sure you understand it, not memorize it. Now, I'll tell you to learn a couple of trends. First of all, the pK, it's good for you to know, of an alcohol is around 15 to 16. Just knowing kind of where it's at, just based on functional group alone, not what's connected to it. The pKa of a phenol is around 10, okay? So already, which one's a stronger acid? A phenolic compound, right? Now, I wanted to show you this chart because it's good to kind of refer back to. You're going to probably use it for some of your homework problems in the textbook. that sort of thing. If I need to provide it to you on the exam, I'll provide the table for you. Like I said, no need to memorize it. But as you can see here, you can kind of compare and contrast, just like if you look at two different compounds and look at their relative pKa's. For example, this tert-butyl alcohol has a much higher pKa relative to ethanol, right? So there's something weird going on here, and we're going to talk about it. But hopefully you see already here that there's a lot of sterics. Sterics obviously has an adverse effect on acidity, and we'll explain why that is. Now, if we move down the table and we look at, for example, ethanol versus trifluoro ethanoic acid here, as you can, or this kind of substituted trifluoro ethanolic compound, not trifluoroacetic acid, my apologies. You can see there's a definite distinction between here and here, right? The substituted trifluoroethanolic compound has a much lower pKa and therefore is a way stronger acid. So there has to be something to deal with this substituent. So there's going to be substituent effects playing a role, something to do with electron withdrawing groups. Okay, so remember how I said, make sure you understand chapter 16. It's going to help you from here on out. This is what I'm talking about. Okay, and like I said, don't memorize. Make sure you just understand why. Understand those structure-property relationships that I'm going to go into in the next few slides. Okay? So you can derive it on your own. It's all relative. You know, which one's the stronger acid? It's all relative. Now, simple alcohols are about as acidic as water. Alkyl groups make an alcohol a weaker acid than water, for example. And the more easily the alkoxide is solvated by water, the more its formation is energetically favorable. So, for example, when we mean by solvated, we mean water. Let's see, there we go. Those hydrogens are partial positive. This anion is partial negative. So if we can stabilize the anion with a bunch of water molecules, it will be a much happier anion, more stable, right? So this kind of here that I'm showing you here is solvation, where water is stabilizing that anion. Now, can water have a chance to get close to the anion if all these methyl groups are kind of blocking its way? No. This is sterically less accessible. It's more hindered and therefore less easily solvated. So this anion is not as stable. This anion is more stable. And you're like, okay, Dr. P, you're talking about the strength of the acid. I can see that you have the pKa of methanol here and the pKa of tert-butanol, but why are you talking about its conjugate base and its stability? Remember that I've talked about this before. The strength of the acid is determined by the stability of the conjugate base. It's so critical you understand that. By the conjugate base, in this case, we're talking about the alkoxide anion, so we're going to talk about the stability of the alkoxide anion, or the phenoxide anion if we're talking about a phenolic type acid. Okay? Very important that you understand that. So you're looking at the conjugate base, you're not looking at the acid itself. The reason for that is the acid will be a stronger acid. It wants to donate a proton if it can make a more stable product, right? So if it can make a stable product, it's more willing to lose that proton to do so. Okay? Now we saw earlier with that trifluoroethanolic substituted compound, the electron withdrawing groups make for stronger acids. The reason why that is electron withdrawing groups make an alcohol a stronger acid because it stabilizes the conjugate base by spreading out the charge over a larger volume. Remember, electrons love to be delocalized. thus making the alcohol which is the conjugate acid, more acidic. So because this electron is, or these electrons are delocalized because we have all these electron withdrawing groups based on the inductive effect, right? It's like pulling those electrons are spreading over a larger volume. A more delocalization makes for happier electrons. Whereas here, the electrons, these are what type of groups? They inductively donate electrons. So that charge is more localized on that atom. That does not make for a very stable anion. So that's the reason why the acid itself is much weaker compared to this one. You see a huge difference. More fluorines attached. Makes it for a very strong acid. Okay? Now, remember, alcohols are weak acids. It requires a really strong base to form an alkoxide, such as sodium hydride or sodium amide or Grignard reagents. We'll talk a lot about these. And the reason why this is important, like I said, is because we use alcohols as some sort of intermediates in synthesis and that sort of thing. So you're going to see this show up a lot. And so you need to know what kind of base to use. Basically, when we react a strong base with an alcohol, what we're doing is generating an alkoxide. And alkoxides are bases that are used as reagents in organic chemistry. So this is not really a product that we're going to keep. We're going to actually take it further and treat it as a base or treat it as a nucleophile in the substitution reaction, like SN1 or SN2, right? So they're used as synthesis intermediates. Now, what I wanted to point out here is, not all bases will work with, alcohols. You need to make sure you choose the correct base. And the reason, the way we do that, and I went over this in the first semester of organics, so if you don't remember it or you feel fuzzy on it, please come see me. But the way you know if a reaction will proceed is if you look at the pKa's of the acids and compare. Compare apples to apples. Don't look at pKa and a pKb. That just gets too confusing. So, for example, the pKa of ethanol is 16. Right? About 16. And the acid on the other side, so I'm comparing the acid. This is a base, so I don't care about that. This is a base. This is the acid. The pKa of ammonia is about 36. Which one is the stronger acid? Ethanol or ammonia? Definitely ethanol, right? So therefore, ethanol is going to push the equilibrium away from itself because it wants to lose that proton. This acid over here is not strong enough to push it in the opposite direction. So definitely, if we react sodium amide with ethanol, we are going to see a reaction. Okay? However, if I did the same reaction but not with sodium amide, let's see if I use sodium bicarbonate, which is a base you use often in organic, right? That would make the products of that reaction would once again be the sodium methoxide, conjugate base, plus carbonic acid, right? The pKa of ethanol is 16. The pKa of carbonic acid is around 6. Which one's the stronger acid? Definitely carbonic acid. And it's going to push the equilibrium back towards the reactants. So if you try to react ethanol with sodium bicarbonate, will it proceed forward? No. Sodium bicarbonate is not a strong enough base. And for the most part, neither is sodium hydroxide because we make water. The pK of water is about 15, so you're not going to get a reaction that goes very far. So it's really important that you learn that there's other strong bases out there besides, sodium hydroxide. A lot of times people are like, it's sodium hydroxide because that's what I learned in Gen Chem. But we're going to work with even stronger bases, such as alkali metals, sodium hydride, sodium amide, and even some Grignard reagents. We'll get to play a lot with Grignards, which are my favorite. So kind of a little bit of review. I did go over that material in general chemistry, in general chemistry, but also in the first semester of organic. Let's talk a little bit about phenol acidity. You notice that phenols are stronger acids than alcohols based on that table I showed you. The pKa's, remember, phenols are about 10. The alcohols are 15 to 16. And the reason why that is because the phenoxide ion is stabilized by resonance. Ooh, you better get good at your resonance structures if you don't feel comfortable with them. We can actually use sodium hydroxide to react with phenols because remember, the pKa of water is about 15. The pKa of phenol is about 10, that will push the equilibrium to the right. So it's safe to use sodium hydroxide. Remember, alcohols do not. What's really good about this is that we can form what's called a salt, right? This is a kind of an ionic force here. And the salt is soluble in dilute aqueous solution. This is a very common reaction we see all the time. Why is it important? And what kind of laboratory technique would you maybe want to make this soluble in water? Extraction. Good. For example, this group here is not soluble in water. Even though it has an alcohol group, that aromatic ring is pretty big. And aromatic rings tend to stack, right? So it makes it more difficult for them to be, pulled apart and make soluble, right? However, if we do a basic extraction and create the salt, which has an ionic force in it, or an electrostatic attraction, this will be soluble in water, which is good because then you can pull it into the water phase and maybe leave another organic compound behind in the organic phase. Remember, extractions, you have test tubes and you'll have 2 layers, and depending on which layer is more dense, that will be the bottom layer. Which layer is not as dense will be the top layer. Let's just say this is our organic layer, and this is, if it's ether, for example, and this is our aqueous layer. We may be able to separate this compound from another organic compound by pulling it into the aqueous layer, doing a basic extraction. It's a very easy way to purify, quick and easy, before running a recrystallization or a column chromatography. And so you always want to do extractions to help you out there. Okay? I want to make sure you have that link together. Sometimes the American Chemical Society does ask about laboratory techniques and how they relate to the theory you've learned in my class. It's really important you understand what you're doing in lab, that you're not just cooking in lab, that you understand how you're synthesizing, how you're purifying. I wanted to also point out there are substituent effects that affect the acidity of phenolic compounds. If you have phenols with nitro groups at the ortho and para position, that will make that acid so much stronger. Actually, it makes it, have the pKa around 7.15, which is pretty significant compared to a pKa of 10 of phenol, right? So the reason why that is because we can draw more resonance structures. This is the conjugate base, right? And that conjugate base is definitely stabilized by resonance. You can see here the phenoxide anions only got about 5 resonance structures. We have 1, 2, 3, 4, 5, 6 resonance structures. It makes it more stable. And I challenge you to draw all the resonance structures You can always ask me in class to check your work for the ortho nitrophenol or the nitrophenoxide anion. I don't care about phenol, I care about the anion, the conjugate base, and meta. Because you notice I said specifically if the nitro group is in the ortho pair positions. I want you to draw the resin structures for the ortho-substituted nitrophenoxide anion and the meta-nitrophenoxide anion and be able to justify their pKa's. You can look up the pKa's for the phenolic compounds based on the stability of their conjugate base, which in this case is going to be dominated by the resonance effect, right? And then finally, we're going to stop right here. We're going to pause the video. Based on the following data for the isomeric 4-carbon alcohols, there's data for the boiling points. How might you account for this trend? So I'm going to pause the video here. You can check your work with me on the next video when we start again. But think about it. I didn't really talk too much about this, but I want you to think in terms of structure. Really try to apply, draw the structures out. Why does 1-butanol have a higher boiling point than 2-methyl-2-propanol? And then next time you watch the next lecture, you can check your answer with me. Okay? Make sure you're reading the textbook. You're practicing the homework problems up until this point. Write down any questions you have so you can ask them during work session time or during office hours. And I will see you soon. Good luck studying.